In this final video in our series on object-oriented languages, we make sure you're familiar with the concepts of aggregation and composition, and that you're aware of three of the fundamental design principles of object-oriented programming. Up until now, we've talked a lot about inheritance, and you can think of inheritance as a is-a sort of relationship. For example, a cat and a dog is a animal, or is an animal. They're inherited from. A plane, a car and a train is a form of transport. But inheritance isn't the only way of looking at how we can tie objects and classes together in object orientation. We can also think of association. Association, very loosely and broadly speaking, can be thought of as a has-a relationship. So, for example, a student has a teacher, and a teacher has a student. A player has a coach, and a coach has a player. The difference here is that these items are completely independent of each other. A student can exist without a teacher. A coach can exist without a player, and vice versa. Aggregation is a more specific form of association. This happens where a class is a collection or container of other classes. However, the contained classes do not have a strong dependency on the container class. If the container class is destroyed, the associated classes still exist. We can see that here. We have a head of department. This is a collection or container class, and it has an association with a classroom teacher. Many classroom teachers can belong to a single head of department class. However, there is not a strong dependency. If the head of department class is destroyed, the classroom teachers can still exist independently, and this is signified by the clear diamond signal. Composition is a much stronger form of association. A class is a collection or container of other classes, just like before. However, this time, the contained classes does have a strong dependency on the container class. If the container class is destroyed, the associated classes are also destroyed. So here we can see that the building class is a container class and has classrooms associated with it. And the classroom class is part of or belongs to the building class. Buildings have a classroom. Classrooms have a building. But this time, if we destroy the building class, the classrooms can't exist on their own. And this is signified by the solid diamond symbol. So you can see here we have this different way of associating classes and objects in object orientation other than inheritance. On the left we have what are weak associations. The classes do have associations with each other, but they can exist entirely independently. We have aggregation, where there is a much stronger association, but once again, the container classes can exist outside of each other. And there's composition, that's the strongest relationship, where if this class is destroyed, the classes contained in it would also have to be destroyed. It's also important to understand the three object-oriented design principles. Principle 1, favour composition over inheritance. Principle 2, encapsulate what varies. And Principle 3, program to an interface, not implementation. Let's take a look at each in turn. So Principle 1, favour composition over inheritance. So in general, composition, which we've just looked at, is preferable in object-oriented design than using inheritance. The reason for this is it allows much greater flexibility. Composition is much less rigid than the relationships that exist under inheritance. An object might be composed of several other objects, but in a real-world sense, it wouldn't make sense to say they inherited all their characteristics. So here, for example, we have a strong association using composition, and we have a building. A building has a door, has a classroom, and has a corridor. And this class is made up or contains these other objects or classes. Some typical pseudocode would be shown here. We can see a class defined for building, with a procedure for creating the building, setting the name and getting the building name, and then a number of private attributes or fields for this building class. And you can see that this class is going to have 4 classrooms, and they're going to be of type object classroom. The second principle is to encapsulate what varies. The basic concept here is that if something varies, it should be pulled out and placed into its own class. We do this as much as possible in order to reduce the need for testing and to aid in ease of maintenance. What you do when you're designing is you take properties and methods and you subdivide them and subdivide them again into as many classes as are needed to make sure they're a true reflection of real-life scenarios. So for example, we may be modelling a school environment and writing a program to manage all the people, students, teachers, admin staff that attend a school. We'd probably start with a simple class like person. Well, we can easily see that this class is definitely not specific enough. We need to encapsulate separately stuff that varies. Well, there's 2 very obvious and very different types of persons who are at a school. There are the students who attend the school to learn, and then there are all the other adults who work at the school. So, we encapsulate what varies. You wouldn't stop there though. Encapsulate what varies requires you to keep going. So, for example, another logical step when you're designing may be to say, well, we have all employees who work at the school, but they fall into 2 main categories. There's teachers who teach our students, but then there's also a lot of non-teaching staff, support workers, cleaners, admin, office staff, site staff, catering. And again, we encapsulate the information that's specific to each because it varies. You'd keep doing this process as far as you can. The final principle is programming to an interface and not an implementation. So this basically means you're focusing your design on what code is doing, not how it actually does it. It's quite possible that we could easily have many different classes or objects which all need to share a similar set of messages, procedures, functions and methods. Yet at the same time, those classes might have absolutely no relationship whatsoever. To solve this, we can program to an interface, and you should think of an interface as a collection of abstract methods that have no actual implemented code written yet. The specific classes can then implement the interface, and they add the how code to each method. It might be better to look at this abstraction. So we have, for example, an abstract interface called switches. We know that all switches will need to have a procedural method to turn them on and turn them off, possibly to set a timer and find out the remaining time. But there could be many different implementations of this interface, themselves not related, but each of them implementing the switches interface. So for example, we could say class heating controls implement switches. The heating control would now be a concrete implementation of the switches interface, where you would add the specific code for this class. Remember, an interface is purely a declaration of capability. There's no actual implementation of code. An interface can't do anything without an implementing class.